Hi, so we are back after 2 weeks, and last time we started about database organization as files, and now we are going to start with buffer pools. Now, last time we saw that how databases are just files on disk, and uh, you just read these files very efficiently and write to these files very efficiently, and just make sure that you are keeping your bookkeeping about what data you're storing and where you're storing it. So we're going to start with buffer pools. What are buffer pools? Buffer pools are just caches for your files on disk, which are lying on disk. So you bring those files into memory and you place them in the frames in the buffer pool, and then you hand back the pointer to the execution engine to perform read writes and do any logical operations. Because storage manager has just the knowledge that your data is just plain bytes. You're writing bytes in and out of the system, and the manager has no logical ordering in its system that it's writing tuples out, or it's writing index pages, or it's writing filters, or it's writing hash tables. But these logical orderings are to be maintained in the by the execution engine. So execution engine requests pages from the storage manager. The storage manager fetches that and hands back the pointer. And then the execution engine makes the logical sense of the thing, that if you are stitching back to tuples or not, or if you're like traversing a B tree, or you are traversing a hash table, or any other type of index. Is it a skip list, or it is a binary tree? So today we are going to start with the buffer pools and what purpose they serve. But let's first talk about caching. So buffer pool is a big cache. It's just a cache for your on-disk pages that you bring from disk into memory, and then you hand back the pointer to the execution engine. So when we talk about caches, we talk about two localities, spatial and temporal locality. So what is a spatial locality? Spatial locality is when uh, assume you have an array. So if this is an array, so spatial locality says that if you're accessing index 0, then you're likely to access index 1 also. You might be traversing the array. And what spatial locality says is that data that is lying close by tends to be used together. So caches can fetch that data for you preemptively. Like if you request page one, and the buffer pool might fetch page two for you because they are lying close to each other. That is spatial locality, and another one is temporal locality. That is, if you're using one page, let's talk in terms of variables. If you're using a variable, then it is tended to be used again. So think of a for loop and the control variable. Let's name it I. So that I variable is good for temporal locality because you're just using that again and again to increment it. But that also introduces a bunch of problems, that how do you invalidate caches between CPUs? But that also holds true for buffer pools as well, that if you're holding a page and someone modified it, then should other transactions see it? Or should I flush it first? Or should I or notify the system that this page has been modified or dirtied? But we'll talk about that. So there are two types of controls in the buffer pool. The storage manager can be aware of the spatial control, that pages lying close to each other, the storage manager can fetch them together, even if you have not requested them. Let's say you have just requested one page, page one, uh, but the storage manager knows that your heap files are just unorganized files, so it can fetch page two and three for you, which might be helpful or it might not be, depending on what your query is doing. Then there is a special temporal control, that if you are bringing pages into memory and assume a page is lying in memory, then how frequently are you using it again and again and again? And like if I'm pulling pages out of the buffer pool to write to the disk or to evict, then uh, what pages am I choosing so that I can evict them from the buffer pool? So being smart about that can also help in temporal control, that you're not evicting some hot page that is being requested. Because if you start writing, let's assume that we have some celebrity, like let's talk about Instagram. Let's say Instagram was running out of a one Postgres server, and you have Taylor Swift's, like it's very impractical example, but let's say you have Taylor Swift's account and you bring that page into memory, and your buffer pool algorithm evicts that after one write. So people keep writing to it. So you write that back out to disk and then you bring it back in. So you're just doing this back and forth for no reason. So a better algorithm would be like to evict pages based on least frequently used, or you can just use a clock algorithm. We'll talk about that also. I think we talked about that. No, we did not. We'll talk about eviction algorithms also. But this is what we are going to study. So you have the disk, you have your database pages lying on disk, and your buffer pool is living in memory. And you bring pages out from the disk into the buffer pool, and then you hand back the pointer to the execution engine. This is what this diagram shows that you're doing that process. So you have the database file. So execution engine says get page two. The buffer pool contacts the storage manager. So now the buffer pool manager, buffer pool manager, and the storage manager are together solving this problem. So the buffer pool manager requests the storage manager that I need to fetch page two, and then the storage managers goes ahead and reads the page directory. The first page directory is brought into the buffer pool, then it is read, and then it is figured out that what is my page size, what file I need to jump to, and at what offset I need to jump to. And then you find the page two, and then you bring it back, bring it to one of the frames, and then you hand back the pointer. So we're going to skip over this. So each empty slot in the buffer pool is called a frame. Uh, you can think of it as like you have paintings on the wall, and you put those are empty frames and you just put pictures in that. So buffer pools are just empty frames and you put your file pages in that. So usually what happens is that most of the open source systems, they just have one setting for buffer pool sizes, that you can define your frame sizes equal to the page size you are using, because assume you have page sizes of 4 kilobytes and your buffer pool frames are of 8 kilobytes, then of course your buffer pool page frames can take 2 pages, but at the same time you have to maintain this overhead of maintaining bookkeeping that this particular frame is holding which pages. Like if there is a one to one mapping between pages and the buffer pool frames, that is much easier to maintain. So usually most of the open source systems just have this one setting that for one database you allot a buffer pool and you decide on the page sizes freehand, like before deploying the database. But bunch of enterprise systems, they give you this flexibility where you can choose your frame sizes depending on individual tables also, depending on individual databases, and depending on individual indexes also. So they give you this more, they have these more bells and whistles that you can do all these modifications. You can choose your page sizes depending on a particular table. Let's say you have a table which is read heavy. So you would like your page sizes to be large because then you can fetch more data in from one page. So if your workload is write heavy, then you would choose smaller page sizes because then you are not writing out 1 megabyte pages for just 10 bytes of updates. I hope it's making sense though. So, what kind of buffer pools are there? We have sorting and join buffers. Those are buffer. So we have a bunch of different buffer pools which serve very specific purposes in our database system. So you can think of it as like your RAM is being divided into different sections by the database system. So the database system mallocs a bunch of memory, and then on a higher level, it just segregates that into different type of buffers. So there is a sorting and join buffer. These are used for sorting and join operations. Like if you join two tables or you're doing an order by clause, those buffers are used. Query caches. Then if you run a query and it produces some result, then you can cache it in data in your memory itself. You have maintenance buffers, like when you run full vacuum or you run vacuum, then if you might need to store the table you are reading temporarily in some storage. So there's the maintenance buffer for that. Then we have log buffers that when you are writing logs out to disk, like you're writing a wall ahead log, then you might need some storage on your memory. So you have a buffer pool dedicated for that. And then you have this dictionary caches. So assume you have a hash table and you you would like to look up a key, but you don't want to compute that key again and again. So you maintain special dictionary caches to just pre-compute your hashes and store them there. Yeah, there are all these kind of buffers which serve different purposes, and in enterprise systems you can modify these also. That you can specify what size I want this buffer, what size I want that buffer. But usually the system decides it for you, unless you are deep into databases and you know actually what you're doing. So yeah. So what we'll cover today is we'll study about Bufferpool Manager, and then we'll try to study about memory mat files too. Uh, yeah. So this is what we were looking at, that your pages are lying on disk, and what you do is you bring pages into frame. So the execution engine, there's the execution engine. The execution engine requests a page, and then you read a page from the disk and bring it to a frame, and then hand back a pointer to the execution engine. But you also have to ensure that how nobody is swapping out that page while my execution engine is doing stuff. So assume that my execution engine has requested page 2 and I have brought this page 2 into frame 2. Now I need to make sure that while execution engine is doing stuff on this page 2, I do not swap it out with some other page. My eviction algorithm does not just evict this page. I need to pin it. That is the official term for uh, specifying that this page is being used in database system. You pin that particular page, and when the pin count goes to 0, then you just know that it is available for eviction. So dirty pages are not buffered, dirty pages are buffered and not written to disk immediately. That's a write back cache. Now there are two types of caches, we know that, write back cache and a write through cache. So what a write through cache does is when you write to a cache, you write through it and you write to the original location as well. So let's say in CPU terms, I read a variable. Let's say I have a variable A and it is cached in my L3 some level of cache, CPU cache. Okay. So when I do a write operation on that, first I write through the cache and then at the same point I also write it to the memory as well. What a write back cache does is you write to the cache first, but you do not immediately write it to the memory. You wait some time and you need to ensure also that that value is not lost. But you wait some time and later at some stage you can write it back out to the original memory. So yeah, so a buffer pool is a write back cache. So what is a write back cache? That when you're modifying a page, let's say this is my page and it's lying in the buffer pool. I modified some portion of it. I do not immediately write it out to disk. I wait some time, I keep it in memory, and at some point, some background process will write it for me. Uh, this might not make sense right now, but there are policies. There is a steal policy and there is a no steal policy. That uh, do you want to write steal pages from the buffer pool and then write them out to disk, or you don't want to do that? But we'll get to that also when we study about recovery algorithms. But yeah, just know that buffering your dirtied pages in Bufferpool and not immediately writing it out to disk is a better choice than just forcing. Like when I write, I also persist it to the disk. That might be slow. That is very slow, and actually, because then assume that you're just doing the write operation. You're writing all these pages out to disk, and then my transaction aborts. Then I need to redo the undo those all the changes that which I did on the disk, and that might be a lot of work for the database system. I'm jumping ahead of myself right now, but yeah. So this is what we saw, that page 1 is being brought into memory, then page 3 is brought into memory. Sorry. So, uh, how do you track the metadata of what pages are lying in a buffer pool? You maintain a page table. So the pin I talked about, that uh, assume my execution engine is doing some stuff with page 1, then I need to maintain a pin counter that somebody is reading this page and I don't need to swap it out. So you maintain an internal data structure, page table, that is in the volatile memory. You don't persist it because you can always rebuild it back up when once the database system is restarted. You can just bring pages and then you can do your page table build up. So what page table stores? It stores a bunch of metadata like the dirty flag that has someone written to this page. Then it stores a pin counter that how many execution, like if three queries are running, then they will and they are accessing the same page, then they will pin the page three times. So there is a reference counter that how many people are actually referencing this particular page. And when the pin count goes to zero, then you know that this page is available for eviction. Then you have access tracking information that what transactions might be able to see this page, what transactions might not be able to see this page. This comes in when you are doing multi-version concurrency control or some other type of concurrency control you are trying to achieve. But yeah, we'll look like we'll see about that also. And what is a page table actually? It's nothing but a fixed size hash table that has been protected by latches. So in database terms, latches and locks are different. So locks are something, they're essentially the same when you implement them, that you would write a mutex, and you could write a mutex for locks also. But what I'm trying to explain is that you have two concepts. One is a latch and one is a lock. So a lock in database terms is used to protect some higher level structure. Like how do I explain this? Assume you have a table and you are trying to update a row. So what you'll do is you will hold a lock to that row on a logical level. What a latch is, that assume you have a B tree on the disk, a physical data structure. When two threads are trying to access it, you hold a latch to that. You don't hold a lock. So a latch is associated with the physical data structures. So I hope I'm making sense. But a lock is just a, a protection mechanism to protect structures on a higher level, like tuples, like columns, like rows. But latches are just for physical data structures where raw bytes are written out. We'll discuss about that also, that what are locks and what are latches. And I hope I have a better explanation at that time. But yeah, so this is the pin I was talking about. That a pin is maintained. That do not swap out this page, and yeah, that's what we saw. I don't think there's anything new in these slides. Okay, so this is what I was talking about: locks and latches. So let's read this particular line. Locks protects the database logical content from other transactions. So the same example I gave, like on a disk level, there is no notion of a table. You're just writing bytes. But on a higher level, by the execution engine, you have a notion of a table, a tuple, and a record. So if you have multiple transactions running and they are trying to modify the same tuple or the same table, then you need to maintain this concurrency control mechanism, the locks, that protect some data like the logical structure, so you don't end up in an inconsistent state. So if you're not getting the intuition behind it, just uh, the takeaway is that the lock protects just the logical structures like tables, tuples, and rows and columns. But latches, let's talk about latches. Now, what a latch does is, a latch will protect physical data structures, and these are not for the transactions. These are for our internal writer workers or the reader workers that we deploy. So these protects the critical sections of the database of database's internal structures from other workers' threads. So uh, the latches. The latches are what we did as database engineers, right? Locks need, okay, we'll discuss about this also. This needs the entire video on its own. But this is a very interesting concept, that what are locks and what are latches, and it's kind of a philosophical point of view, like not a philosophical point of view, but it's more of a intuition based thinking, that you understand why there are two terms, that one is a lock and one is a latch. So we'll get to this also. So a page table versus a page directory. So what is a page table? A page table is an internal structure which is maintained, like metadata about the buffer pool and what pages are cached in the buffer pool. But a page directory is the information metadata about the pages lying on the disk. It has nothing to do with the buffer pool in the main memory. All it has to do is with the data lying on disk. So is a mapping from page directory is a mapping from page IDs to page location in the database files. So essentially what's lying on the disk, it's just a metadata. Uh, Page table is a mapping from page IDs to a copy on the buffer pool frames. So essentially what is lying in the RAM. So you can blow away the page table. So it says that this is an in-memory structure and does not need to be stored on disk. You can blow away the page table and you can rebuild it back when you come back up. But with the page directory, you cannot blow it away. You have to persist it if you're doing changes, and because that is the metadata about the data. So if the metadata gets corrupted, then you might not be able to interpret what's lying in the database pages. So let's get to MMAP. MMAP is a very interesting thing. Uh, I think last time I saw LMDB. LMDB. LMDB was using MMAP. So LMDB stands for Lightning Fast Memory Map Database. No, something along those lines. Lightning Memory Map Database. I think something along those lines. But Andy also discussed about it, that he said that everybody is telling you that do not use mmap. The LMDB guy is saying that always use mmap. Now, why do we don't want to use mmap? So, for those who don't know what mmap is, mmap is a system call that the operating system provides to you, where you can map your files on disk into your process's memory and then read and write to that file in such a way that you are just writing to another memory location. So there are two semantics. So one way is to just do a fopen. You get a file descriptor and then you use that file descriptor to do the changes. Another way is to memory map the file. So the operating system will just memory map it for you, and then it will hand back you a pointer to a memory address, and then you can just treat it as if you were writing to some memory location in the heap. So why does memory map come into play? So let's do an analogy. What we are doing in the buffer pools, we are bringing pages from disk into memory. So we're bringing files into memory, and then we are handing back to the back pointer to the execution engine. What I said about mmap, what mmap does is it brings files into memory, and then it gives back you a memory address pointer, and then you can read and write to that pointer. Now, there is some analogy between that why do I need a buffer pool when mmap can do that same thing for me, that is bringing pages into memory or files into memory and handing back me the pointers. The problem with mmap is that with buffer pools, we have total control over the system. That when I'm bringing pages into memory, I decide what pages are being affected. I decide what page need to stay, what pages are pinned, what pages are not pinned, what pages are available for eviction, what pages are dirtied, and what pages are not dirtied. I build this whole infrastructure to just maintain metadata about what pages are dirtied and what the internal system is, like internal state about the pages is. With mmap, Assume you bring in some file into memory and you memory map it. You write to that file. Now you don't have any metadata. You can maintain metadata, but the operating system is free to write that file back out to disk because you used mmap for it. You don't have control over mmap. So you cannot say that I want to go into the operating system, modify the mmap, and maintain, like, then you are just doing equivalent work to building a buffer pool. What mmap does is it brings files into memory. So you have files mapped on in your process in memory, but now you have lost control over what files are being written out to disk. So the operating system is free at any time to swap out pages and just decide that uh, this file page is not needed anymore and it will be swapped out. So I hope this I think I gave a good analogy about why memory map and buffer pools come into play, then what is the debate about. And to be very honest, the very first thing I thought was that mmap was a good option. Like when I was studying back, when I was getting introduced to databases, I was like, why you're doing buffer pools when mmap can just map files? But then I figured out that yes, you have lost control. You if your database crashes, then I won't go into recovery, but what happens is when you modify a page in the buff pool, you also write ahead log, but you ensure that the write ahead log is first flushed only after that your pages are flushed. So you ensure, only after that you say to the transaction that you have committed. So I'm jumping ahead of myself again, but we'll get to that. Okay, so let's talk about mmap now. So OS mapping use OS map memory mapping to store the contents of file into address space of the program. OS is responsible for moving file pages in and out of memory, so DBMS does not need to worry about it. So you don't have to worry about writes or reads. If the database system allows multiple threads to access mmap files to hide page fault stalls. So another problem with mmap is that when you request a page and it's not in memory, the OS will page fault you. That it will give you a page fault, but it will not show you that it's page faulting. It will page fault in the background, and while by the time it goes and gets that page, your thread has to just wait for it. So you're wasting cycles, CPU cycles waiting on the process as well. So let's compare it again, okay? So we have a buffer pool, we have a mmap. Now some thread, let's say this is my thread lying above in the empty space. This is my buffer pool, this is my this is my mmap. Now I have used one system uses mmap, one system uses buffer pools. My thread is trying to access uh, a page in the buffer pool. Let's talk about buffer pool first. So say I have multiple threads running, and in my buffer pool, I have threads trying to access a page, but that page is not in the buffer pool. So what my buffer pool will do is it will tell that thread that this page is not in the buffer pool, and I will get it for you by the time you might want to yield and let some other thread take control. So what that does is in a very concurrent system, it saves you CPU cycles that you know that this page is being fetched, and you can swap out that thread, make it sleep, and wake it up when that page is available. Let's compare it to mmap. What mmap does is when my thread is requesting a page and it's not in memory, my operating system will never tell me that it's page faulting. It will page fault, but on a kernel level. So it will page fault and it will go and fetch the page from the disk. But my process will never know that my CPU is page faulting and I might need to switch. It will just keep waiting there and burning CPU cycles and not let any other thread take control. So you can see how that is like just wasteful because the OS is just hiding all these page faults from you. You have no idea what it's doing underneath the hood. Okay, so we can see that page one is brought into memory. That when I requested page one and it page faulted, it is brought into memory. Then my virtual mappings are updated to that physical page. Uh, if you do know about page tables, the OS page tables, there are two level of page tables. Then the MMU walks that page table to convert virtual addresses into physical addresses. This is that when I bring pages into memory, I also change the virtual mappings and then I give control back to the original thread that's requesting. So I need to do all this work and not tell the thread that I'm doing all this work. And the thread just assumes that it's doing valuable work, but underneath the hood, it's just wasting CPU cycles. So yeah, this is showing that. So this sleeping guy is telling that my thread is just waiting. So let's walk it through. So assume I my thread wants page one. Okay, so my thread wants page one. Uh, my okay, so the mmap, the OS will bring page one into memory. Okay, then it will update its virtual mapping, and then it will ha hand back control to my thread that yes, this is page one for you. Let's say I request page 3 again, and then I brought page 3 into memory, updated my virtual memory, and then I gave back control to the thread right here. But now my physical memory is limited. I don't have infinite RAM. So let's say my thread requested page 2. Now this physical memory is full. What OS needs to do right now is it needs to swap out pages. That it will take page 3 or page 1 out, bring page 2 in, and then update the virtual mappings and then give back control. But to the thread, it looks like that it is doing some good work, like it's doing some actual productive work, and it just needs to wait. It does not need to give control to some other thread. So by the time CPU does the fetch, the thread is just waiting. It needs to sleep and it needs to yield and give control to some other thread to do maximum CPU utilization. But the problem with this is that the CPU, the operating system is just abstracting away any errors and any page faults that are getting. So, memory map problems, transaction safety. That when, let's say, multiple transactions are running and you touch pages which are memory mapped, the OS is free to write those pages out to disk anytime. So, the OS can flush dirty pages at any time. So, then there are IO stalls. The page fetching we talked about, that when your physical memory is full and you need to swap out pages and bring some other page in, or you need to fetch a page which is not in memory, then you are not telling your thread to sleep. Your thread is just waiting there for you to fetch that memory, fetch that page, and then update your virtual memory addresses and then hand back the pointer. Database system does not know about what pages are in memory. The OS will still stall a thread on page fault, and it will not tell it that it has stalled it or it has put it to sleep. So you can see how we have lost control. But as I said this line that the OS will stall a thread and we will not about know about it, the OS might tell that thread if it is a not a user level thread, it is a if it is a kernel level thread, then the OS might put it to sleep. But you can see how that is also a problem because in the modern programming languages, every programming language comes with a runtime. So if you run Go and you compile it, it comes with the runtime embedded into the binary itself. And it manages that user level thread that you're running, the Go routines. And the OS cannot touch those. The OS can only put kernel level threads to sleep, not the user level threads. So I hope you can see that how that is a problem as well. I just realized that I can write an article on this. But anyways. Then you have performance issues that when you have TLB shootdowns. What is a TLB shootdown? It's a translation look aside buffer that when one process is the CPU switches one process to jump to another process, it just flushes its TLB. TLB is what? TLB is a cache for the page tables, not the database page tables. It's the cache for the OS level page tables, the virtual memory, the MMU walkthroughs that we do. Those page tables are cached in the TLB, those addresses. So when you context switch, you flush those TLBs, and if you context switch too much, then you might be just incurring the overhead of TLB shootdowns, that your TLB is being invalidated and some other entries are being brought in. So you might do this very frequently. So, um, what database systems use MMAP? These systems use MMAP. LMDB is a very famous one that it is based, its name is based on memory mapped, I guess. Lightning mapped database. You need to search it, but it uses MMAP very heavily. Then we have LMDB, sorry, Level DB, which was out of Google. RocksDB, which was written by Facebook, was forked out of Level DB. And the first thing that RocksDB did, like the guys at Facebook did, they threw out mmap. They built their buffer pool and they threw out mmap. So the Google guys somehow decided that they will use mmap. Then MongoDB very famously used mmap in their first versions, but then they bought WireTiger, and now they use a buffer pool. So one very good analogy that Andy gives is with MongoDB, the amount of cache they had and of the amount of money they had. If they cannot do it with a map, nobody can. The amount of resources that were available to them, if they could not figure out a map to a very efficient way, what chance do other guys stand or the open system stand? So never use a map. So if you do decide to get on with a map, then there are some system calls for you. So there's M advice for you, where you can tell the OS that you can tell the OS. Just a second. Okay, so uh, M advice, where you can tell the OS that what pages are advised to not be flushed. Like you can tell that I need this page, hold it on priority, and don't flush it. But the OS is free to ignore your advice under heavy load. Like if it is full of, like your system is running under heavy load and your RAM is full, then it might affect pages. Then you can also do an mlock that tell the OS that memory ranges cannot be paged out, that some memory range starting from this to disk, don't flush them out to disk. Then you can do a msync to flush. It is your counterpart to fsync, that when you're writing and you want to ensure that what you have written is persisted to disk, then you can do a msync for that. So these are just msync is just a counterpart for fsync when you do it when you have opened a file with fopen. So when you're doing all this madvice, mlock, msync, then what you're doing is you are maintaining this extra overhead. You have started writing a buffer pool itself. You have to maintain some metadata, that what I need to msync, what I need to mlock, what I need to madvice, and then along the lines you start realizing that you have started building buffer pool with mmap. So why not build a buffer pool without the mmap? That would be a better idea. So these slides show that these all systems have moved out of mmap. MongoDB, as we called that, wire tiger was introduced into MongoDB, and most of the system, like above, Elasticsearch is just an in-memory store, so they can use. But yeah, so the OS is not your friend. The OS will try to hide things from you. So as Linus says that users don't know what they are doing. We as kernel developers, we know that what's best for you. But as database engineers, I'm no one to say that, but Andy says that we are database people and we know what we are doing, and the OS is down, and the OS does not know. So, so I think if it was up to him, he would just take away the operating system entirely and just use raw file systems to just write database files to disk. So Andy also has written like a bunch of alumni of like no. They have written a paper on why you should not use MMAP. There's also a video about it. Let's see if they have pasted the video. Yes, this particular video. This is on YouTube. You might want to go and look at this. So this video is about some guy buying MMAP from some shady guy on the street and then putting it into his database and then realizing that what a mistake it was. It is a good animation to watch. Not sure what this comment is though. I'm 97% certain this is because the faster code leads to more page trashing in mmap based index readers. I'm gonna have to implement my own buffer pool and manage my reads directly like that. Vex that is okay, said all along. So I think this is some guy on hacker rank, I guess, realizing that they should not have used mmap and just should have used buffer pools all along. So we have buffer pool replacement policies, but we will start with this next time because this is as long as I can record. We'll start with replacement policies next time. That how do you evict pages from the buffer pool? And yeah, thank you for watching.